Hi, in this presentation, we'll focus on how we've integrated Elasticsearch at Traackr and how this architecture has allowed us to efficiently scale our search cluster and maintain high availability during migrations. So just a little bit about myself. My name is Bryan Warner. I'm the lead software architect at Traackr, which is a leading influencer marketing and analytics platform. I've been working in the software industry for almost 20 years now and worked in search for almost a decade. Mostly during my time at Traackr. We were pretty early adopters with Elasticsearch at Traackr. We started on version 0.9 to be exact, so it's been pretty cool to see the community and the technology evolve over the years. A little bit about Traackr. Traackr aims to be the system of record for influencer marketing, empowers the influencer programs for some of the world's top brands, such as L'Oreal and Revlon. Customers leverage Traackr in many capacities, but with regard to search, I wanted to call out three functional areas. First is influencer discovery. This allows our customers to search our global influencer data set by published content, influencer attributes, and audience demographics in order to surface the best potential partners. This relies heavily on keyword-based search and custom relevance scoring capabilities provided by Elasticsearch and Lucene. Also, there's campaign reporting. Customers can measure the performance of online campaigns to identify top performing content and influencers by specific KPIs of interest to the brands, such as engagement rate by influencers and performance over time. This reporting is customer driven as they are managing hundreds of campaigns across thousands of influencers. It relies heavily on the aggregation framework in Elasticsearch for visualizing the different KPIs. And finally, there's market benchmark. So customers use this to understand how their brand and competitors perform among all influencers in a given market. This reporting is produced internally by Traackr and relies heavily on complex keyword Boolean expressions to generate and categorize the reporting data set. So a little bit about our search cluster. We are on the open distribution of Elasticsearch on version 7.17 to be exact. We are deployed in AWS EC2, and we manage all the nodes ourselves via Terraform and Ansible. Our production cluster is 50 nodes currently, and we have a little bit over 10 terabytes of data. We have our document count is a little over 7 billion, and we have around 450 indices. Our index topology is unique to our business needs. So our primary search index is our global index for storing influencer documents and all the related content. This takes up the majority of our storage capacity and overall document count. This index is the most taxed as it powers all of our real-time search capabilities, plus it's the source of all data for report generation pipelines. We also have many reporting indices allocated on dedicated nodes to power our advanced reporting analytics. Influencers and posts are identified via the primary search index by a complex set of keywords and filters, and then run through a custom ETL pipeline that categorizes, enriches, and stores this data in Elasticsearch in these reporting indices. Because reporting nodes typically serve a lot of aggregation-only queries, we dedicate more memory to certain caches like the shard request cache on these nodes. So Elasticsearch is the analytics backbone that powers all of Traackr real-time search capabilities and reporting analytics. So we really have two mandates as an engineering team from the business. The first is to maintain a highly available search cluster that can scale to suit our data growth and functional needs. And this is more than just adding nodes, but it's really being able to redistribute our data over more shards when the time comes, to being able to split indices in certain cases, and even making low-level schema changes to mappings and analyzers. So for instance, at Traackr, because keyword-based search is very important to us, we've customized the behavior of the standard tokenizer in Lucene and how it tokenizes different punctuation. So being able to efficiently A/B test those changes and roll back if necessary is really crucial to the success of our business. Second, the data to ensure customers always have access to the data they need, we want to integrate our data with Elasticsearch in resilient and fault-tolerant workflows. The data we store in Elasticsearch is derivative of various upstream data stores, but it's important that this data is kept in sync in a timely manner so customers always have access to the search and reporting capabilities in real time. Yeah, so how do we meet those business mandates as an engineering team? In order to do so, we subscribe to the following 3 pillars. The first is an event-based architecture. The second is data portability. And the third is monitoring and measuring for success. And just as a backdrop, this past year, Traackr's engineering team completed a major migration from version 6.8 to version 7.17. This effort also involved scaling our search infrastructure to accommodate higher data growth and achieve a more sustainable shard size across our data nodes. Listed here are the goals for this migration. We'll dive into these more later, but we'll use this migration to show how our 3 pillars allowed us to meet these goals and allows for success as a business. So let's dive into the first pillar, which is event-based architecture. So in case folks aren't familiar, event-based architecture allows us to decouple responsibilities between services by way of events. This is a simplified view of a producer-consumer model, but it's very representative of what we do at Traackr. On the left, we have services and data stores that might want to send their data to Elasticsearch for use in search and reporting. On the right, we have consumers of that data that want to transform the data into the necessary document schema and handle any failure conditions. And it's all facilitated by an intermediary, which in this case is Apache Kafka, which in case you're not familiar with Kafka, you can think of as a durable transaction log for events. We deploy Kafka as a managed service in AWS, which is great for high availability using a clustered setup, and allows for some cool features like auto scaling in case the amount of data we're sending is unexpected and we need to scale up the underlying data store. Topics in Kafka are generally configured with message TTL. So depending on how long you want to live this data, how long you want this data to live in Kafka is dependent on your business use case. But really, Kafka's only goal here is to be highly available to facilitate data workflows between producers and consumers. So services on the left can send events manually to a topic. Like for instance, if there was a record changed or a certain condition was met, they can send the necessary payload and that will get stored in the event topic. If you can also use Kafka Connect to automatically sync a database source with the Kafka topic. For instance, like if you have a simple rule that every time a database record is created or updated, you want to send it to Elasticsearch. This makes not having to do all that manually in code. So each approach has its pros and cons, and we use a mix of both approaches, but it just gives you a better overall flexibility for how you want to get this data into Kafka. On the consumer side, and let's use the service Y that's outlined in blue. So the consumer will fetch a batch of messages from the topic and create a corresponding bulk indexing request. We'll send that, and if the cluster responds successfully, we can then acknowledge the batch and the consumer offset, and Kafka will be updated. And the offset is basically the timestamp for that given consumer of the last successful message processed by that consumer. So if, for instance, if service Y crashes and restarts or restarts, it needs to know from which point to start reprocessing in the transaction log. If in the example when it sends the bulk indexing request, if the cluster responds with a failure, like say the cluster status is red, then the consumer doesn't have to acknowledge that batch of messages, and its offset remains the same. So basically at the next retry interval, it will reprocess the same batch of messages, and if the cluster's green, it can succeed and continue on processing the transaction log. So as we can kind of see here, this really greatly increases the data resiliency when integrating your data with Elasticsearch. Producers of indexing events don't have to concern themselves with the state of the cluster and know about different indexing failures or cluster states. We can optimize the indexing performance in a distributed microservice environment. For instance, it would not be very performant if each service was sending lots of little indexing requests, but instead the consumer can batch everything and send an efficient bulk indexing request instead. And as you'll see later on, it promotes flexibility in replicating writes across new cluster setups. So for instance, in this diagram, you'll see that there's a service C outlined in green, and this could be like a new cluster that we might be also sending new indexing requests to in the term during the process of a migration. But we'll circle back to that later. So yeah, let's talk about data portability. Again, data portability is not a great term, but it's just the ability to move and migrate your data quickly and efficiently. We really want to strive for predictable and consistent cluster migrations and understand the levers that control data restoration and reindexing speed, because delays at this stage could lead to an increased risk of downtime to your users, or even complications trying to catch up your new cluster with new events. I'm assuming most folks are familiar with the restore and reindex APIs. There's a lot of great documentation online and best practices, so I'm not going to repeat that here. And I assume most folks are using this restore snapshot APIs to back up their cluster daily. If not, you definitely should. But I'll just want to go through some lessons learned over the years of using these different APIs. To start with the restore API, for greater restore throughput, definitely tweak the cluster setting that is the recovery max bytes per sec from the default 40 megabytes to whatever matches or whatever your hardware can tolerate. So for instance, like on new cluster setups, we usually increase it to like 500 megabytes, and we can restore 10 terabytes of data in less than 30 minutes. Some folks don't know about that default setting, but you can really just, you should greatly increase it when you set up a new cluster and you're restoring data. Once we have restored data, we're basically, the restored data might need to be reindexed if we're changing the number of shards or we're changing the underlying mappings or analyzers. For greater reindex throughput, definitely recommend to enable slicing to parallelize that reindexing process. Basically, you set the number of slices to control the number of threads underneath the covers. Elasticsearch usually recommends setting the number of slices to the number of target shards in your index, the number of shards in your target index, which is a good rule of thumb to follow. But definitely be aware of who is coordinating the reindex request. We definitely recommend using a dedicated coordinating node with enough CPU memory to coordinate highly parallel reindex requests. It's something we, in a previous migration from version 5 to 6, I believe, the reindexing process took a lot longer than expected. And when we dug into it, we realized that the node that was coordinating the reindex request with a lot of different threads was becoming basically, it was having its CPU pegged. So it just took a lot longer and was something we didn't think about ahead of time. So I definitely recommend using a coordinating node. And as always, if you use stored scripts, if you're going to be rewriting mappings via the reindex API, just so each thread doesn't have to parse and compile the script source. Yeah, we'll also talk about, let's talk about monitoring. So, with any major migration, it's critical that you're able to observe the impact of the changes introduced and how they'll positively or even negatively impact your end users. I think it's a bad assumption that every major version upgrade will benefit your specific usage of Elasticsearch, so you really have to monitor and measure this. And as always, invest in monitoring tools to collect key resource and functional metrics. So at Traackr, the set of tools we use to facilitate this are Telegraph, which is a metrics collection agent, InfluxDB, which is a time series database for querying metrics, and Grafana, which is a visualization tool for graphing metrics and data. These are just the tools we chose that we feel gave us the most flexibility in our observability stack. These can be very well replaced by the ELK stack that Elasticsearch offers. It's very similar, but it's just the tools we use. So each Elasticsearch node runs a Telegraph agent for exporting metrics for like health, CPU, CPU memory metrics, or even active indexing and search requests, as the graph shows there. And while the metrics exposed via the Elasticsearch APIs are great, they're pretty low level, and it's hard to distinguish between the various types of queries your application might generate. Like perhaps some parts of your application might utilize heavy aggregations versus other ones are doing a lot of keyword-based searches. So I highly recommend that you instrument your client search code with various functional metrics, tagged by various dimensions, like for instance, like the user context. It just gives you a better glimpse into how your search queries are performing, and just allows you to drill down based on these dimensions and just get better visibility in your system overall. So yeah, once monitoring is in place, we can then measure the performance of our new cluster and whether we've met our goals. So first, you have to have goals, which are very important to define ahead of time. And you need a framework to conduct A/B testing. So we at Traackr follow the green-blue deployment model, which is pretty well documented online. We have built-in capabilities over the years to route search traffic for individual users, accounts, and even environments to specific search clusters. I wish I could dig more into that during this presentation, but I just don't have the time, unfortunately. But definitely recommend that as part of your doing that as part of your application. We also leverage open source tools for replaying search traffic against new clusters, to help simulate load. Like for stress testing, one, for instance, is goreplay.org, which we found to be very valuable, because usually when you set up a new cluster and you restored and re-index data on that new cluster, your new cluster isn't doing much. So it's good to stress test before, to maybe identify any issues before you start to, transition traffic into your new cluster. So yeah, let's put all these, things together and see, how, these three pillars in action. So this is the playbook we used during our migration to version 7, and we kind of broke it apart. We broke it into 3 separate phases. So we have a prep and setup phase, a data restoring catch-up phase, and a testing phase. So the first one is, prep and setup is usually the easiest. We, spin up a new cluster on the given version 7, using Terraform and Ansible. We perform a snapshot of the existing cluster, and then we record the timestamp marker of the last Kafka indexing event to be included in that snapshot. And so why do I bring that up? Because once the snapshot request is initiated, any subsequent indexing events written to the existing cluster won't be included in the snapshot. And so those events need to be replayed on the new cluster. So we need to make note of that, that timestamp in the transaction log. So usually takes 1 to 2 hours, or usually takes like an hour or so. The data restore and catch up is usually the long tail of this playbook. So we're going to restore the snapshot on the new cluster, again, tweaking that recovery setting to allow for faster restoration speed. We, once the restored data is there, we can reindex the restored data. And in this case, we were changing the number of shards, and we were also changing some of the mappings. So we needed to set up new indices with those new settings and reindex the restored data to them. We dedicated a beefed up coordinated node to handle the reindexing process, and I think we used like a concurrency factor of over 40. I thought it was a little higher, but maybe it was around 40 to do all that reindexing in parallel. Yeah, so once the data was restored and reindexed, we could catch up the new cluster with any indexing events produced after the snapshot was taken, which is usually pretty quick. So again, we spin up a new consumer to read from the indexing event topic in Kafka. We tell it to start reading events from the timestamp marker that we recorded in the first phase, and then basically can catch up. And then once that's done, we have 2 clusters that are in sync and both receiving indexing requests via 2 separate Kafka consumers. And then we can proceed to the testing phase, which is really just conducting A/B testing and trying and looking out for any functional regressions. Testing did reveal, in this case, testing did reveal 1 minor regression due to changes in version 7 that require script scores to be non-negative. We had updated our code to account for this change, but there was a minor edge case in production that was producing a negative score, and our test just didn't have enough sample data to catch this. So luckily, it was an easy fix, but it was it was, we were able to catch it before, porting customers over to the new cluster, or porting customer traffic over to the new cluster. So once we conduct our testing, we can shift some search traffic to the new cluster and monitor key resource and metrics. And then once we felt confident there were no major performance or functional regressions, we could switch all search traffic to the new cluster and continue to monitor. And then eventually, after some time, usually between like 12 and 24 hours, we usually shut down the old cluster and then tear it down. Yeah, so we can take a look, did we meet our goals? And we definitely did meet our goals during this migration. So at the time, we wanted to migrate around, this 6 million documents, 300 indices in under 24 hours with no downtime to our end users in business. So we were able to meet those goals. We were able to reduce the utilization metrics on our primary index by over 50%. So like CPU, load, disk IU, memory. And then in the case of like average response times of various searches, like the parents-child searches we use in influencer discovery, as well as like the content aggregation searches that are used in reporting, we were able to reduce those by, we were able to exceed the target reduction. And I think a lot of it was due to the better distribution of data over more shards, but also we were pretty impressed with some of the memory improvements in version 7. For instance, like the memory footprint was greatly reduced with respect to various caches like the field data cache. So we just saw a lot of overall improvements and healthier nodes going to version 7. One goal that we didn't hit, unfortunately, was we were hoping to see a better hit to miss ratio in our query and request caches. We saw that there were some improvements in version 7 with regards to scripts being cached better, but that didn't seem to translate in the metrics we were recording. We haven't yet quite diagnosed what's going on there. And here are some of the just the graphs from from Grafana to kind of drive home the point. So these are like the 1 month before and after the migration of our search API metrics in certain contexts. So in the top left, we're measuring like post-aggregation searches, which are used heavily in our reporting functional areas. And then the bottom right is the parent-child searches, which are used heavily in influencer discovery. So we were able to greatly reduce the average response times and just kind of minimize the overall kind of spikiness that we were seeing before. Yeah, so thanks for listening. If you're interested in learning more about Traackr, you can follow us on Twitter. If you want to learn more about how customers leverage Traackr, you can read our blog, or if you have any technical questions or just want to dig more into the slides, you can feel free to send me an email. So thanks.